So our final presenter in this session is Madeline McIntire. Madeline McIntire is a second-year master's student at the University of Vermont in ancient Greek and Latin. In addition to ancient languages, Madeline enjoys keeping up with breakthroughs in physics and playing viola in orchestra and chamber ensembles. She plans to teach high school Latin following graduation. Yay! Okay, put in a plug for that. So her paper today is entitled, A Greek and Latin Reader on the Heliocentric Universe.
I think I know how to do this. Just double tap on this.
No, it's actually downloaded. It's a great.
Oh, thank you.
And we'll do
This slide. Great, good morning. Thank you for the kind introduction. So today I'm presenting on a pedagogical project that I made last semester that's intended as a resource for the history of science that also stretches a student's abilities in reading original Greek or Latin. So a reader is generally a selection of passages from a larger text that's supplemented with grammar notes and biographical and historical information. So for this project, I chose to feature passages from several ancient and early modern authors that all center around one theme, and that theme's the development of the idea that the sun is at the center of the universe and not the earth. So the layout of the reader, it opens with an introduction, a very brief introduction with contextual information on the four authors that I feature. At the very end is a vocabulary list tailored to the passages I include. And then I have four authors, Aristotle and selections from Peri Uranu on the heavens from 350 BC, Ptolemy and his work He Megale Syntaxis, which is, you could translate as the Great Arrangement. It's more commonly known by its title, the Almagest, which comes to us from the Arabic, from the 2nd century AD. And then we jump ahead many centuries to Copernicus, De Revolutionibus Orbium Caelestium in 1543, and Galileo and his pamphlet Sidereus Nuncius from 1610. And I'll go through each of these authors as we go along. So each of these writers developed influential models of Earth's place in the universe. Aristotle and Ptolemy concluded that Earth was at the center of the universe. And this idea dominated scientific thinking through late antiquity and the Middle Ages. Copernicus and Galileo famously supported the idea that the Earth orbited around the sun. So these four authors are often mentioned in physics or astronomy courses, but there's rarely time to read their original writing in class. My intent with this reader is to enable students to read the scientific texts in their original languages and think about how science builds over time through the contributions of different thinkers. So I begin with Aristotle, because he presented a model of the universe which dominated Western astronomy for about 2,000 years. So he imagined the cosmos as a set of nested concentric spheres with Earth at the center. So you can see that over here on the left. The one on the right is just a prettier rendition of the same model. So perhaps on this big screen you can see it's Earth at the center with little paths and mountains. And then we go to the orbit of the moon, the orbit of Mercury, the orbit of Venus, orbit of the sun, and so on and so forth. So these are all in the genitive because it's the orbit of such and such a planet. So Aristotle imagined that this outermost sphere was stationary and contained the fixed stars, and the inner spheres were each responsible for the motion of a planet. So I include a passage that argues why Earth is at the center of the universe. Aristotle thought that massive objects would naturally fall to the center, and Earth is massive, so it ends up at the center of the universe. Claudius Ptolemy worked in Alexandria, Egypt in the 2nd century AD, and in his Almagest, he gives a mathematical account of the orbit of each planet using geometry, which marked a significant break from the Babylonian tradition of predicting the motions of the heavens using arithmetic. So he had a similar structure to Aristotle in terms of thinking of the heavens as a set of nested concentric spheres, so we can keep this image in our heads while we're thinking about Ptolemy. His book formed the foundation of medieval and early modern astronomy, and it was the first in history that we know of that offered tables for calculating the orbits of planets, the sun, and the moon at any past point or future point in time. So I included in the reader a passage that advocates mathematics as the most reliable way to describe the workings of nature, because I thought it was an interesting early argument for the importance of math in scientific discovery. And I also include a passage that mentions that the planets revolve in circles. So it's not the most exciting thing, but it does show this idea of circular orbits. So one interesting distinction between the methods of Aristotle and Ptolemy is that Aristotle sought to make a model of the cosmos that described its physical reality, so how these spheres fit together and what they were made of. Ptolemy was trying to make mathematical predictions about natural phenomena, so predicting when eclipses would happen and when Venus would rise and set. But he didn't venture to model how it was actually put together, like the physics of it. And the division between natural science and mathematics was typical of ancient Greek and Babylonian astronomy, and it wasn't really until Copernicus's day that mathematics was thought of as a way to describe physical reality. And in fact, it was the discrepancies between the Aristotelian cosmology and Ptolemaic astronomy that spurred Copernicus to introduce a new solution. So Copernicus was a clergyman in East Prussia, modern-day Poland, educated in Italy, and he also imagined the heavens as a set of concentric spheres. So it wasn't until Johann Kepler that we got the idea of elliptical orbits. Copernicus's famous innovation was to put the sun at the center of the universe and make the Earth one of its planets. So here you can see at the center the sun, and then we have the orbit of Mercury, orbit of Venus, and then Terra, Earth. And then it says Tellurus is the orbit of Earth. And the planets go out from there, and he did have a sphere of fixed stars on the outside as well. Copernicus drew heavily from Ptolemy's data to form his heliocentric theory. The data wasn't completely accurate, it had a lot of measurement errors. It was also hundreds of years old, but it's important to note that Copernicus's theoretical insight was made possible by all that data that Ptolemy had collected some 1,400 years earlier. So that's why I think it's interesting to read these authors side by side. They didn't develop their ideas in a vacuum, they were building on the thinkers who'd come before them. And then finally, I close with Galileo Galilei and his pamphlet, The Starry Messenger, or Message. You can translate nuncius either way. It's more commonly spelled as nuntius in Latin textbooks. And this here is the frontispiece, declaring that he has discovered the Medicean stars. That's what he chose to name the moons of Jupiter. So I decided to include Galileo's discovery of the moons of Jupiter because it was an important piece in cementing the heliocentric theory. So Galileo doesn't actually discuss the fact that the sun is at the center of the solar system in this pamphlet, but his discovery of moons around Jupiter opened the possibility that things don't have to orbit the Earth. So if Jupiter has moons of its own, it means that heavenly bodies can have different centers, so that it opens the possibility that Earth can also be rotating around something else. It's significant that Galileo chose to write this pamphlet in Latin, unlike his earlier Italian publications, because it shows that he was hoping that this publication would reach an international audience. So this is an example of what the reader looks like. I have a printed copy if anyone would like to see it afterwards. But each of the pages generally have this format. So I have a title at the top, the author, the title of the work, and the section that it's from. Then a passage of the original text. So for Aristotle and Ptolemy, this is in Greek. For Copernicus and Galileo, it's in Latin. And then horizontal line, and then notes on grammar and historical context. So I haven't used this project in a classroom yet, so there are doubtless places where additional notes could be added to improve the ease of reading the text. I just added notes in places where I could anticipate a student getting stuck. So anticipation isn't a foolproof method for knowing where to put notes, but it's definitely a start. So for example, a student might wonder, why is prohibeat subjunctive? So that's that fourth word in the Latin up there. And so I give a note for cum, and I say, try translating it as although. It's a concessive cum clause, so it takes a subjunctive verb. So hopefully speeds up the translation process for the student. Another thing I tried doing was rearranging the Latin or the Greek words in a way that was close to English word order. So the very bottom comment, I say, try the following word order, which is close to the English. So this is corresponding with the second line of original text up there. Ut possit una errantium siderium existimari. So I found the syntax a little potentially complicated for an intermediate student, so I rearranged the Latin words into something that's closer to our syntax. Terra possit existi mari, una errantium siderium. The Earth is able to be thought as one of the wandering stars, that is, as one of the planets. So I did this to keep students in foreign language learning mode, so not switching directly to English, but still helping them get in the right direction of making a translation that's satisfactory. In hindsight, I probably would not assign Ptolemy in the original, or even include it, because the prose is very convoluted and elliptical, and I had to gloss lots of the sections in English because they just, unless the student had probably 3 or 4 years of college Greek, it would just probably be too difficult. But I would assign a chunk of his text in English to give students a sense of his writing style and the opportunity to read his words in the original. It's like reading a science textbook from 2,000 years ago. It's quite something. This is the vocabulary, so it's arranged by author and section so that you can assign just one bit. Say I only wanted to read the part from Aristotle 2.4 from On the Heavens, and it's alphabetized to speed up the translation process. And then I've also included a few images when I thought it would assist a student in understanding the text. This is particularly important for Galileo. He included sketches of Jupiter, and its moons. So here on the left we have the abbreviation for Orientalis, the east, and on the right-hand side we have an abbreviation for Occidentalis, the west. So it's 2 good Latin words. The large circle is Jupiter, and the little asterisks, or the little stars, are the moons. So Galileo observed these on successive nights, and he saw that they were exhibiting strange behavior. So one night, 3 were to the west. And then another night he went back, 1 was gone, and 2 were to the east. And so he watched this pattern repeat itself, and he eventually realized they were orbiting Jupiter, and he was looking directly at the plane of their orbit. So he correctly conjectured that these were satellites of Jupiter. So they're important to understanding the text, but the images also give you the sense that you're looking at a scientific notebook, which is a special thing we don't often get to see from hundreds of years ago. And it lets students think about what the scientific method looked like at different points in history. So the intended audience is anyone with upper intermediate to advanced skill in either language. I would say the Greek, on average, is more difficult for these 2 authors than the Latin are. For Latin, I'd probably recommend that students have a year of Cicero or Virgil under their belt. And if I were in a Latin-only classroom, I'd provide translations of the Greek or vice versa so that you can see the continuum of these thinkers over time. And some of these texts were hard to access in the original, especially the Ptolemy and the Copernicus. The only way I could access Copernicus in his original Latin was through a book in UVM's special collections. So that diagram I showed you with the sun at the center is actually a photo I took from that book. So I was fortunate to have that resource, but a lot of people don't have access to that sort of thing. So my hope is that this reader will make the text accessible for Latin students who are interested in sciences perhaps, and Latin students who might not have gone anywhere near a history of science otherwise, but might take an interest in it if exposed to it. Thank you for your attention.
writing what we call the Dark Ages, someone asked him, why are the days of the week the way they are? So in his Latin encyclopedia, he says the days of the week are dedicated to the Romans, how they named the days after the stars. And the first day is Die Solis, then Dies Lunae. So what's interesting to me based on that is it seems that there might have been a dichotomy between educated Greeks and Romans and the hoi polloi on the ground. Because ordinary Romans aren't saying the days of the week the way they probably did. They're saying Die Solis, Dies Lunae, Dies Mercurii. So I'm wondering if that could be something to explore further. Like, why would millions of Romans not use the current scientific method of the order of the stars and the spheres for their own days in that sense?
That's very interesting. That could also be a nice appendix to add on. Thank you.
I was wondering about the languages you found. So I was wondering if there was any passages you didn't find representations from good God and yourself, or if you found any that somehow something that doesn't line up with Greek or Latin, or the lines.
Oh, that's a good question. There are actually very similar versions for finding, especially models for the Aristotelian model of the cosmos. There was one I toyed with that was like a three-dimensional cutaway with the spheres, and you can kind of see the crystalline structure. I don't know, I'm going to keep it 2D. And so I went for clarity here. Most of the fun ones, the fun diagrams, had too much going on. Like some of them had the astrological symbols for the planets instead of the actual names. And one that was just like a ball and stick diagram. But yes, there were plenty of pretty images. I did try to use ones that were older when possible, like the photo of the Copernicus model of the universe, since that was right from the text I was copying. I thought, well, that's a good thing to include. They also have a little more personality when the sun has a face, and you don't generally get that on the representation.
I just want to say that I think it sounds wonderful, and I'm thinking in my head about all the opportunities for collaboration between a Latin teacher in a school and maybe a high school science teacher, maybe, teaching complementary lessons, or feeling that, just having a science teacher there to give commentary as we read it. And I think sometimes we do get so set in our department, and we don't always get out there and kind of go teaching to our schools, so this is such a great opportunity for something like that.
Definitely, yes. And this space is easy to get people excited about, so that's another. Dan has a question.
Yes, the image of the moons of Jupiter from the Galileo text,
Yes.
it seemed to have east and west orientations reversed from what I would normally expect to see on a regular map. Is there a reason for that?
That's a very good question. I don't know, actually. But I'll have to look into it. Thank you for mentioning that.
Is it upside down?
It's not upside down. Or my photo's not upside down.
The telescope lens might not have been.
I wonder if it was the way he was looking through his telescope.
Yeah.
To his left would have been the east, and to his right would have been